Find the zeros of f of x equals negative x cubed minus 2x squared and state the multiplicity and behavior of each. In order to find the zeros, as we previously stated, we need to factor this. So let's take negative x cubed minus 2x squared equals 0. And factor this. We can factor out a minus x squared, which leaves behind an x plus 2, close parentheses, equals 0. Now we can set each of those equal to 0. Negative x squared equals 0, or x plus 2 equals 0. Now the exponent on this x squared actually tells us the multiplicity. So this first one, if we solve negative x squared equals 0, we see that x equals 0 with a multiplicity of 2, because it is squared. Now the other equation we have, x plus 2 equals 0, shows us that x equals negative 2 with a multiplicity of 1, because it is an x to the first power. Now notice, if you sum those multiplicities, if you say 2 plus 1, we get 3. Well, the original equation was a third-degree polynomial. That's a way we can check our work. Now the behavior at each of these, at a multiplicity of 2, it will, as we said, it will touch, and then it will bounce off the x-axis. A multiplicity of 1 will cross. It will cross the x-axis. Right, our next example says to find the zeros of f of x equals x to the fourth minus 4x cubed plus 4x squared, and state the multiplicity and behavior of each. Again, we'll set this function equal to 0, because that is what a 0 is, the value that makes the equation equal to 0. We'll factor out a greatest common factor of x squared. So we have x squared times parentheses x squared minus 4x plus positive 4 equals 0. And that will factor, so that we have x squared, and then x squared minus 4x plus 4 factors to be x minus 2 times x minus 2, which I'm going to write as x minus 2 squared, because now I can see the multiplicity here. Each of these have a multiplicity of 2. So the first of these, x squared, when I solve that equal to 0, or set it equal to 0 and then solve it, I see that x equals 0, and x minus 2 equals 0 would tell me that x equals 2. And each of those have a multiplicity of 2, which means both of those touch the x-axis and then bounce going back the other direction. As our picture showed previously, something like that, or potentially, depending on how it comes into that, it's going to bounce off in that same direction. Our next example says to find the zeros of f of x equals x to the fourth minus 8x squared minus 9, and state the multiplicity and behavior of each. Well, this is actually a polynomial in quadratic form. So this will factor as x squared and x squared, and then we need two numbers that multiply to be negative 9 but add to be negative 8, which would be a minus 9 and a plus 1. And I should say I set the original function equal to 0, then it factors as x squared minus 9 times x squared plus 1, still equal to 0, so we can actually not set those equal to 0. Let's factor more. This first factor becomes x plus 3 times x minus 3. It is a difference of squares. And then x squared plus 1 does not factor. This first factor shows us that x equals negative 3 with a multiplicity of 1. The second factor shows us that x equals 3 with a multiplicity of 1 again. That's an x to the first. Now the third factor actually doesn't tell us any zeros, because if I take x squared plus 1, set it equal to 0, this would mean that x squared equals negative 1, and the square root of negative 1 is plus or minus I. So I have two zeros, positive I and negative I, but those aren't actually going to show up Okay, so while these are zeros, let me just say this. While they are zeros, they don't have a multiplicity. Well, actually they do. They have a multiplicity of 1, but they don't show up as x-intercepts. So we're not going to worry about those when we get to the graphing part of this. But if you notice, you add those up, add the multiplicities up, 1 plus 1 plus 1 plus 1, 4, which is the degree of the original function. So those imaginary roots actually do play a role. They just aren't very useful for graphing. All right, for our next example, find the zeros of f of x equals negative x cubed plus 2x squared plus 4x minus 8. As we've done on every one of these, I'm going to set this equal to 0. So negative x cubed plus 2x squared plus 4x minus 8 equals 0. But in this case, I'm going to factor by grouping. The first two terms have a minus x squared in common, which when factoring that, we get an x minus 2 factor. The second two have a positive 4, so plus 4. Oh, actually, let's go back. Let's first factor out a negative 1. Let's do that first. If I factor out a negative 1, that leaves me with x cubed minus 2x squared minus 4x plus 8 equals 0. And then I can factor by grouping. Have just a positive x squared, and that leaves us with an x minus 2. And the second two will take out a minus 4, which leaves us with an x minus 2. And I'm going to leave that minus sign out here for a little while. Leave it factored out. Now, factoring by grouping, this would be x squared minus 4 times x minus 2. Bring down our minus sign, equals 0. And then x squared minus 4 factors as x plus 2, x minus 2. Then we have that other x minus 2. That equals 0. I see two zeros, the first of which is negative 2 from this first factor, the x plus 2 factor. X equals negative 2. And the second two factors actually have the same solution, that is, x equals positive 2. Since those have the same solution, this would tell us a multiplicity of 1. And the negative 2 is a multiplicity of 1, or a multiplicity of 2 for the x minus 2, since there are two factors. Now, if we add those together, that's 3. That is the degree of our polynomial. So that covers all of our zeros. Our next example says find the zeros of f of x equals 2x cubed plus x squared plus 8x plus 4. Find and state the multiplicity and behavior of each. Again, factoring plays a big role, so we're going to take that function, 2x cubed plus x squared plus 8x plus 4, set that equal to 0. Factoring by grouping looks like a good idea. We have 4 terms. So from the first two terms, we'll factor out an x squared, which would leave us with a 2x plus 1. So x squared times 2x plus 1. And the second two, we could factor out a positive 4, which would leave us with a 2x plus 1. So this is going to factor as x squared plus 4 times 2x plus 1. Setting each of those factors equal to 0, we have x squared plus 4 equals 0, 2x plus 1 equals 0. The first equation we have will give us x squared equals negative 4, and the square root of both sides. Taking the square root of both sides, we see that x equals plus or minus 2i. So there we have two solutions, 2i, negative 2i, each with a multiplicity of 1. And the last, we would solve that. Subtracting 1, we get 2x equals negative 1, which means that x equals negative 1/2 with a multiplicity of 1. Again, we have 3 solutions and a degree of 3. Now the behavior at each one of those is that if they are all multiplicity of 1, that we have that it crosses. Okay, so at each of those places, our function is going to cross through the x-axis and not turn back around. All right, our last example for this objective, find the zeros of f of x equals negative 9x squared, parentheses, x minus 4, close parentheses, cubed, times x plus 1 quantity. And then state the multiplicities. Also, determine the degree and end behavior of this polynomial. Well, this is already factored, so I'm going to take each of those factors, minus 9x squared, set it equal to 0. The next factor, x minus 4 cubed, set it equal to 0. And then x plus 1, set it equal to 0. If you notice, we can actually ignore the exponents. It's not going to affect our answer. However, that is our multiplicity. So this one has a multiplicity of 3. This one has a multiplicity of 2. And the last one has a multiplicity of 1. So the first equation results in x equals 0 with a multiplicity of 2. Second, x equals 4 with a multiplicity of 3. And the last, x equals negative 1 with a multiplicity of 1. Now, if we add up the multiplicities, that actually tells us the degree. So that would be a grand total of 6. We have a 6th degree polynomial. If you can also notice that by realizing that this is minus 9x squared. We have an x minus 4, x minus 4, x minus 4, and then an x plus 1. 2x squared, x cubed, x to the 4th, 5th, and 6th. If you add up all the exponents of those terms. Next, we can observe for the end behavior that we have a minus 9, that's a coefficient of x. We have a 1 that's a coefficient of x, and a 1 that's a coefficient of x. So the way we do this is minus 9 times 1 times 1 times 1. Okay, that would be for each of the 3 terms there, times 1, and that is minus 9. All right, so our leading coefficient is minus 9. Putting that together with an even degree, a negative leading coefficient with an even degree tells us that our function is going to fall to the left and also fall to the right.